Shall we start, Suresh?
Yes, absolutely.
Good afternoon, everyone. It's my pleasure to invite everyone to this Knowledge Leadership Forum lecture by Professor Krishnan Suresh, Meadwitter Foundation Professor at UW Madison. I now request Professor Punusami to introduce our speaker for the day. Thank you.
Thank you, Professor Ashok. Good afternoon, everyone. It's my pleasure to welcome Professor Krishnan Suresh. He is Philip and Jean Mayers Professor of Mechanical Engineering at the University of Wisconsin-Madison. He received an MS in Manufacturing Engineering from UCLA in 1992 and a PhD in Mechanical Engineering from Cornell in 1998. He then served as an engineering manager at Kulig and Sofa, Philadelphia, until 2002, before joining the University of Wisconsin-Madison as a faculty. He has received numerous peer-reviewed grants, including the prestigious NSF Career Award and the ASME CAE Excellence in Research Award. His research interests include topology optimization, additive manufacturing, advanced finite element analysis, and high performance computing. He has also co-authored over 95 peer-reviewed papers, two of which have received ASME Best Paper Awards. He has also authored two textbooks on applied optimization. He is a co-founder of SciArt, a UW Madison spin-off that creates and supports high-performance topology optimization software solutions. It's on behalf of our department, I thank Professor Krishnan Suresh for joining us for this scale of lecture. The floor is yours, Professor. Thank you.
Oh, thank you. Thank you, Dr. Punuswamy, for the introduction. Very kind of you. And also like to thank SASTRA University for this opportunity and Dr. Ashok Palaniappan for organizing this event. So it's indeed my pleasure to talk to you all. I will go to my presentation. So I think it'll be good, just from the interest of time, if you want to note down some questions, I'll be happy to take questions. I'll try to keep aside at least 5 to 8 minutes for questions at the end. And this talk is on one of the projects that we are pursuing in our group. Hopefully the topic will be fairly broad, that's of interest to folks outside this area of specialization. So try to keep it fairly general. First and foremost, I always like to thank my students for all the work that they put in, because without them, none of this work would have been completed. I think all this has already been covered, so I won't spend any time on that. I'm right now a faculty at UW Madison, been here about 20 plus years now. I was also serving as a CEO of a startup company in Madison, very briefly. And so just to give you a context of the nature of this talk, I want to distinguish between single scale and multi-scale structures. And I know there are going to be students from outside mechanical engineering, maybe from chemical and other fields, and faculty as well. So I try to keep it very broad. So these are called single scale because all the features are roughly the same order of length. And those are very, very easy to analyze, model, design. Those don't pose any challenges. On the other hand, you'll see a lot of these multi-scale structures, both in engineering and in nature. And those are really, really hard to design them, to analyze. You want to understand flow of blood, you want to understand the turbine airflow, you want to understand the thermal structural analysis of these multi-scale structures, or even designing them is extremely hard. So that's the focus of this talk. But in particular, there's one subclass of multi-scale structures called repeated multi-scale structures. And a classic example, Eiffel, and it's very appropriate with all this Paris Olympics. All of us have got a chance to see, hopefully, the Eiffel Tower. And it's an amazing structure that was designed using multi-scale ideas where you can see repeated structures, truss structures that are put together to form a well-built, well-designed Eiffel Tower. These are called repeated multiscale structures. And you see a lot of this in nature as well. You see these repeated cells put together in some multifunctional form. That's a bamboo structure that you see in nature. If you probe fine enough, you see these multiscale structures. So that's what this talk is about. In particular, I'm going to just state what the focus of the talk is. And I do understand that not all of you are trained in finite element and other related topics, but hopefully I'll try to make it clear. So the talk is on on the analysis and optimal design of repeated multi-scale structures. Hopefully these examples tell you what my focus is on. And in particular, I'm going to focus on this using neural networks. How do I use neural networks and all these buzzwords about neural networks? Are they worth it? How can I use them in real engineering? That's kind of what the topic is all about. So let me explain in a very simple two-dimensional setting. So I have the simple structure, which is fixed at the left and applying a load at the right, hopefully very easy to visualize. And I have some kind of a repeated multi-scale. So I have these little tiny structures that repeat themselves in one or more regions. And this is an example of two microstructures. So what I want to do is I want to account for this fine feature, just like you saw in the Eiffel Tower. I want to account for these fine structures, but I want to predict the global behavior. Unfortunately, trying to do this all in one single shot, trying to analyze the whole structure in one computer run is very, very expensive and very difficult, and also an overkill. You may not want to do that. So the question is, how do we go about analyzing these multi-scale structure? And the key idea, and again, some of you may be familiar with, some of you may not be, but hopefully get the idea of homogenization, which is what I'm going to talk about. Homogenization is very, very simple. It's almost like saying, what is the equivalent behavior? I don't want to know the details of all the things that are going on at the microstructure, but I want to just use the basic behavior of that and use that in a broader context. That's called homogenization. You kind of create an equivalent behavior, and that's called the homogenized elasticity tensor. If you don't know these buzzwords, that's perfectly fine, but as long as you understand conceptually what's going on. So you have these equivalent behaviors. So what you do is you take these microstructures, you analyze them and say, okay, how does this microstructure behave? How does that one behave? And I want to throw away that and bring in the equivalent matrix. So you condensed all this information into one small matrix, and then you put together,
Suresh?
and this is a classic. Yep.
Are the slides moving?
Oh yeah, I'm sorry.
Okay, we're not able to see the slides moving. Yeah. At least I'm not able to see.
You should. Oh, I wish you'd caught me earlier on.
Oh yeah,
I've been
yeah,
talking.
yeah. And can you make it full screen, please?
I did. When you make it full screen, it's not showing, I guess. Is it showing now?
Not yet.
Yeah, let me see. I'm sorry. Does it show now?
No.
Oh, wow. Okay, then we're having a bit of a trouble here.
But the slides are moving now, so I think it's fine. There's a icon at the bottom row, bottom panel. There's one full screen there. Maybe that works. Yeah, yeah.
Does it show?
No.
So the minute I go to full screen, I'm sorry that it didn't show up. I'm going to try sharing a full window.
Okay.
Let me just see. I'm sorry. I apologize. I'm going to try entire screen. So entire screen is not working. And if I share a window and if I share this, so does it, I'm sure it shows up now, right?
Yeah.
But if I go to full screen, it stops?
Yes.
I don't know what's going on. This is a standard approach, I guess everybody uses.
Slides
Something is
are
wrong.
moving. Yeah.
So let me just go with the slides here. So
Yeah,
let me just quickly.
Yeah.
It's fine.
Yeah,
And I'm going to skip all this in interest of time. And I guess you have to go back and rewind the thought process, saying there are single scale and multi-scale structures. My focus is on multi-scale on the right-hand side, which are really large structures with minute details in them. So hopefully, and again, I'm going to speed up in the interest of time. And I was giving an example of an Eiffel Tower. I'm sorry, all this was, I was talking to myself, I guess.
Makes a lot more
The Eiffel
sense
Tower.
visually, yeah.
Okay, now it makes sense. Hopefully, all the talk. So you're looking at Eiffel Tower as an example of a repeated multiscale, and where have small structures being repeated over the entire Eiffel Tower. And that's what I'd like to analyze. And I was giving an example of in nature, you see bamboo with multiscale structures and so on. So the idea is or the question is, how do you analyze and design these repeated multiscale using neural networks? And in particular, I was going to talk about the fact that we're going to take a very simple 2D structure with a couple of microstructures. And the key idea that I'm going to use to analyze this is a process called homogenization. Homogenization is pretty simple. All it says is, I don't want to know the details of what's happening inside each microstructure, but tell me its equivalent behavior. Is it behaving stiff in one direction? Is it behaving stiff in a different direction? That's what I'd like to know. And you can capture this information using a very simple in 2D 3x3 matrix that tells you everything about the structure in a condensed way. So Ashok, everything okay so far?
Yes, we're all good. Yeah, thank you.
Okay, all right. So this is kind of where I was, and hopefully we didn't lose too much time. And I was saying that your job now is to take these individual behavior of each initial microstructure, you put them all together in the classic finite element, and those of you who've done finite element will hopefully recognize these terms. You put them in a global assembly of a finite element problem, solve it, and you get a global behavior. That's called homogenization. So you got rid of all the details and solved the problem pretty quickly. So just to summarize, the first step is you start with a global structure, take each individual microstructure, you homogenize it, put it all together in a global matrix, and predict, for example, how does the Eiffel Tower behave under heavy wind load. You can't analyze each truss beam, but you condense all that and you can analyze how the Eiffel Tower behave under different load conditions. That's the basic idea of analysis using homogenization. What I'm interested in, I wish I could use animation, but that's okay. So there's a lot of material to absorb. What I'm interested is design. When I say design, what happens is you want to close a loop. I want to achieve some goal. I want to design an Eiffel Tower. How do I do that while accounting for all the details? So that's a pretty difficult task, as you can imagine. And the way you do that is in two tasks. So what you see here, I don't know if a mouse appears, but that is my lower level task one. I'll design each microstructure at a lower level, and then I take that all up and design task two at the global level. So in some sense, all you can visualize is when you're trying to design an Eiffel Tower, and Eiffel did not design it that way, but in today's computer era, if you want to design that, you will design each substructure to behave in some optimal way, and then put it all together to design your tower globally. So that's the two-level approach that people adopt, and we can approach it in a couple of ways. So I already told you the homogenization. Given a microstructure, you can get the 3x3 matrix. What I want to do now is backwards. I'm giving you a 3x3 matrix. How do I get the microstructure? That's called the design part of it. So that's obviously much harder. And people try to aim for different types of behavior. I want a stiff microstructure. I want a strong microstructure, and so on and so forth. And you do that through a process called topology optimization. So that's the basic idea of what happens in the design of microstructures. And what I want to give you is, because not everybody is an expert in this field, I want to just give you a big picture. This is a very well developed field now called topology optimization, where brilliant minds like Eiffel could come up with these designs just by visualizing what is going on. Today, unfortunately, we're not that smart. We tend to rely a lot on computers, and we tend to use mathematical tools, do programming, automatically design these structures. And that is the idea of topology optimization. There are various techniques, and I'm going to use one of them called the density-based methods. And I'm going to skip through the details, just saying that it's a process by which we can systematically design various microstructures that are that meet our requirements. For example, let me show you some couple of movies, and I'm skipping the mathematics simply because there is probably extensive. You can spend almost several PhDs on each of these topics. So instead, I'm going to focus on just the ideas. For example, I want to design a particular microstructure that stiff in all directions. You design something like this. It'll automatically design this microstructure and say, that is my best design. So these are tools that are available today. Many industries use these tools. As a different example, this is a microstructure that you'll come up with if you want a different goal. So different microstructures will achieve different goals. And that's the idea of automatic topology optimization. Here's one that is called the Poisson ratio that is completely different in shape. You can hopefully appreciate the fact that this looks very different. So I don't want to emphasize the underlying mathematics and the subtleties. All I want to emphasize is that depending on what you want to achieve, there are tools today to systematically program these things and take away all the mundane tasks of computation and program them for you. Now, what is our research goal in our lab is that we want to do topology optimization like we talked about, except that instead of using classic methods, I want to use neural networks to do topology optimization. So that is kind of the goal. That I'm going to try and walk you through the basic ideas. And again, don't get lost in some of the mathematics and details. Instead, maybe hopefully you can absorb the basic ideas that you can apply towards your own research. Again, if it's can be absorbed at that high level. So if you think about neural networks, they're just a collection of functions you put together in some convenient way. And that's really what a neural network is. It's just a collection of functions with weight parameters and so on. So the way you capture is that at any point x, y in a microstructure, these functions you can manipulate these functions in the neural network to predict whatever quantity that you want to predict inside the microstructure. And that's the basic idea of a neural network representation. And we're going to use that to design what we need. And I'm going to jump directly to the next slide here. So what we're trying to do in our group is, instead of using classic methods of optimization, which people use using meshing and other techniques, which if you're in optimization world, you can implement them in standard methods in MATLAB or Python. But we're doing that using neural networks in our lab. And I can show you some of the differences that we get. So there are some advantages. You can ask, why do I want to do using neural network? And then one of the important advantages of neural networks is that you can get what is called automatic differentiation. And this is a big advantage in neural networks, at least in most of the implementation. That is, let's say you implement a function, right? You can implement a function using MATLAB or Python, but the key question often that arises in design is what is called derivatives or sensitivity. How does a function value change if I change one of the input parameters? That's a very important question in design. You can say, hey, that's trivial. I can do finite differences. I can evaluate the function for different inputs, so I can find out the sensitivity or derivative. Unfortunately, finite difference is not very accurate, whereas neural networks provide you what's called automatic differentiation, which will take the derivative of the function for you automatically. And that is a big deal in design. So this is probably the most important slide, if I can emphasize what this whole idea of neural networks, why do you want to use it in engineering, is that two things. One, the neural networks are really, really rich. I told you that rich in the sense of functional space. That is, if you have I told you it's just a collection of functions, but they're not just ordinary functions. They're highly nonlinear and very rich. You can capture extremely complex functions using a very simple neural network. And that's one of the reasons neural networks have become very popular in machine learning and other fields is simply the richness of the neural network. And that's this part of it. The second part of why neural networks are extremely good in optimization is something that emphasize is automatic derivatives or automatic sensitivity. They let you take the derivatives of these functions automatically. So again, I'm skipping all the details because it may be outside many of your interests and your background. But if ever in your field you want to talk about how do I capture extremely complex functions, whether it's chemical, electrical, or any other field that you want to capture, you may want to consider neural networks and say, can I use neural networks to capture these functions? What do I get out of it? These two big advantages. And that's something you need to keep in mind when you want to use neural networks. So what are the advantages? Let me demonstrate. And again, I'm going to skip all the details of how it is implemented and so on. Instead, I'm going to just show you that it's possible to generate exactly these, what I talked about using classic methods of designing stiff microstructures in different directions and so on. Let me just show you, if you recall, the one of the challenges that we faced was in designing such microstructures. Now, let me just show you. I think this is hidden through an animation. I'm going to take it out. I apologize because that is going through an animation. And using a neural network, you can get extremely complex microstructures. And the goal was to minimize this value. You can see that we've achieved much lower value. And those of you who design these microstructure can appreciate that we went much lower. The lower you go, the better it is to design. And you can see the richness of the design and the details that you can capture, unlike in a classic representation. So that is what this neural network does for you. And you can capture, like I said, all kinds of smooth and non-smooth functions using neural networks. And that's what we're exploiting in our group to design these microstructures. And much of the mathematics is not what I want to focus on. All I want to say is that we can achieve certain goals that is not easily achieved through classic techniques. So we used well-published information or data on how to design these microstructures, and we're able to surpass what has been shown in the literature by a significant margin. And almost 3x to 10x better performance, and all thanks to the neural networks, because they can search the design space and find designs much better than the classic methods. And again, more examples. You don't need to worry about the details, but just illustrating the beauty of designs, that these are completely automated. You can see some of the beautiful designs that these neural networks will generate, and they're all done automatically. In fact, I have no idea how these were generated internally. It just figures out some mathematics internal implementations to come up with designs, and you can do some clever things like extracting really, really smooth neural networks. I'm sorry, the smooth designs using these neural networks, some of the additional advantages that you cannot do using classic techniques. And not only can you do pure structural, and you can do thermal, you can do magnetic, you can do all kinds of other fields that I wouldn't talk to you about. You can do multiple materials. There are very simple ways of doing multi-material. That is, instead of designing one material, I want to steel, aluminum, and tungsten, and I want to combine all these materials, and I want to design a structure. Neural networks will allow you to do that. You can come up with, I don't know if there's a movie. There should be some movies here. Yeah, there we go. And I wanted to show you some additional designs. So these are designs that the neural network is figuring out where to put different types of material to achieve a goal. Right. So I'm not again describing the particular context of what we're trying to design. Those are the details. Instead, I want you to understand that neural networks are extremely flexible. They're very, very flexible in achieving the designs that we want to achieve. And there are some challenges that we see, and I'm just going to point out that there's some post-processing that may be needed to get some islands of material that neural networks, because of the nonlinear behavior, they actually tend to pose some challenges in some aspects. I want to just, in the interest of time, I want to give enough time for questions. So I want to talk about the bigger scale. I talked about the microstructure so far. I want to, pull back and say, how do I design the entire Eiffel Tower now? I've designed each microstructure to achieve a goal, and we've done quite a bit of work on that. And I won't spend too much time. And we've designed all kinds of macrostructures using neural networks, comparing again literature and so on and so forth. We can do this in 3D, but the more interesting are multi-material designs where neural networks are really good at separating out different types of material. It'll tell you you should use steel or some material here, a different material here, a different material here, in a very systematic way. And again, these are things that are going to be relevant as you get more and more into very complex designs where intuition doesn't help you. Maybe 200 years ago, we could design structures intuitively, but today the designs are getting so complex that you cannot rely on intuition. You need systematic and heavy computation, and that's what our group focuses on. We can do, again, these are details about microstructures. I'll just show you some pretty pictures. These are true multi-scale designs. So the neural networks are able to design this very detailed microstructures for you to achieve a goal. They'll tell you where to put what type of material, what should be the thickness to maximize some objective given some constraint on cost, on mass, and so on and so forth. And these are things that are published information. If any of you are interested, I'll be happy to point them out to you. And we started designing now. This is very exciting work, very recent work. We are just published this about a couple of months ago on designing structures that look like nature using Voronoi structures. We're able to design microstructures that can exploit Voronoi diagrams which mimic nature. So we're trying to mimic nature using neural networks. And I can just see if I have any interesting designs. Very, very early work, and I'm not going to go to the details of this. Instead, show some very sophisticated designs. And these are really, really difficult even a few years ago. But today, with all the tools that we have, we can train these neural networks to design multi-scale Voronoi-like structures with all kinds of intricacies built into the design. And we can design fluid devices which achieve microfluidics. And like I said, the physics is, you can cover all kinds of physics behavior from fluid flow, magnetics, to thermal, structural, and so on. And we have tried to 3D print some of these structures to prove that they're indeed performing as we expect them to perform. So again, I know we lost a lot of time in the initial first few minutes, and I also want to give some time for general questions, because these are very, very specific topics that it's almost meant to give you a glimpse of some of the opportunities in using neural networks, hopefully in your research. And I know when Ashok visited us, we talked about some of these opportunities in our different fields, and we just exploited in one particular field in design. So Ashok, I want to just give enough time. I know we have less than 10 minutes. But would you want me to talk a couple of slides on quantum computing? It's up to you.
I think we can like see if there are any questions, and then like,
Sure.
there any questions? Anyone? I had one or two questions, if I may ask myself.
Sure.
That is like in some of the optimized structures that you showed, I think maybe slide 29, it looks like most of these structures are symmetric. They have like fourfold symmetry. Now,
That's correct.
A usual outcome? Is it inbuilt? Some symmetry constraints are added, or this just falls out of the
Excellent question.
process?
No, excellent question. In this particular example, we required equal stiffness in all directions. That was our objective. The objective forced you to take the symmetric design because we said I wanted to be equally stiff in the x direction and the y direction. So the designs that were generated were automatically symmetric. But if I said I want twice the stiffness in the x direction as the y direction, then the designs will not be symmetric.
Yeah, got it. Yeah. So is the fourfold symmetry arise naturally, or you just say equal stiffness? It could have been like a different fold symmetry. So I'm just wondering if it has to be fourfold. Is that a
Oh, good. That's again a very good question. No, we did not impose any fourfold. It just came up to be a good design that it came up with. We did not impose. There might be other designs that are not fourfold symmetry that have good properties, but this is something that the neural network generated, and that may have to do with the way the homogenization happened and so on and so forth. It's sometimes very hard to predict why it came up with a particular design.
okay? Any questions, anyone? I had one more question, if I may.
Sure.
When you mentioned the activation functions, I mean the weights and bias parameterize the density field, whereas the
Right.
activation functions span the field. I
Correct.
was wondering, does that depend on your selection of the activation functions, or would any choice of activation functions span the field?
No, that's again a very good question. So it doesn't matter what activation function you can use, leaky RLU, you can use, the sine hyperbolic, tan hyperbolic, all of them will span, but the designs that you get will depend on your activation functions. So I did not talk about all that in this short slides, but the type of activation functions I choose will influence the design to some extent. And we don't have a good understanding on exactly why which activation function is the best. It's an open area of research, but they will affect your design.
So a lot of subtleties that will arise as we go on with this, right?
Absolutely, very, very good point. And again, these are very uh, tricky areas of research that students get in without understanding some of the subtleties. And we need to step back and say, wait a minute, what activation function did you use? How did it influence the design? And it is very difficult to understand. So the neural networks are both good and bad that way. They're really good, they're very rich, but the richness is also going to affect you because they're so rich that they're highly nonlinear. We don't fully understand their behavior. They're not simple linear combination of functions. Yeah, exactly correct.
Yeah, very interesting. Um, yeah, so there's a question in the chat box, I think.
Oh, I see. Okay,
Shall I read it to you?
could please? I can open it up, but yeah, go ahead.
Alaksha Reddy, a faculty in mechanical engineering, he asked, is it possible to share the licensed version of the topology optimization software to Shastra University? terms of fee payment need to be discussed. Students who are willing to do MS at your university can get good exposure on topology optimization before they come there for MS.
Oh, very good question. A very good point. Two things. One, all our software are free to use for academic purposes. And much of the code in MATLAB, Python are directly linked from our website. So if you go down to this website here, and you'll see all the publications, and next to the publications would be our link to the MATLAB code or Python code that students can download and use it. That's for mostly 2D. Now, if you look at three-dimensional topology optimization, for example, this one here, right? That's a three-dimensional topology optimization. Very difficult to achieve using MATLAB or Python. So everything is done using C++, and we have a plugin directly into SolidWorks called ParatoWorks, which is a topic by itself. And I didn't talk about that today, but we have a complete plugin, and I use that in all my classes. In undergraduate, we teach topology optimization to undergraduates, and we happen to use this software to teach them. The students just love it because they just love the fact that you can just click the button and it gives you an optimal design within 2 minutes. And I've given them a bet and saying, I'll give you $100 if you can beat the design that topology optimization gives you. And the bet is still open. No, nobody can beat it. It's very difficult. So the point is these tools are available, and we'd love to see academic, being used in academic environment to teach students. So if you send an email, I can send a link on how you can download this for use within SolidWorks, and people all around the world are using it today. Hopefully I answered that question.
So one part of the answer is that a lot of these resources are available on your GitHub site.
Correct.
And second is like for these plugins, we can contact you directly.
That's correct.
At ksuresh@wisc.edu.
That's correct. So I can give you a link to the plugin, and you just install it. It'll take less than 30 seconds. If it needs SolidWorks. SolidWorks is a CAD tools that everybody uses in mechanical engineering. And if you have SolidWorks installed, let's say on your personal laptop, you just install the software and just follow the instructions. There is a guide on how to set up problems and design topology optimization. And it's not a commercial tool. It was a startup company. So if you recall all the way that I said I was a CEO, and this came out of that plugin to topology optimization, but that company doesn't exist anymore. During COVID, it ran out of funds, and I was not too keen on pursuing that myself as a faculty. It is run by my students and other CEO that they hired, but it's a technology that was commercialized. So it is used by a lot of companies, but I can make it available to any academic use. I have the right to do that.
I hope that answers the question.
Dr. Suresh, thank you for the presentation.
Go ahead.
I was fascinated by the multi-material optimization, slide 42.
Right.
Yes, this is a very nice result. So, do we get to validate this by some experimental methods, or is there any other
Absolutely.
validation?
No, very, very, very good point. So I've not talked about some of the validation. So we do 3D print this using different materials. We can get different polymers that we 3D print. I did not show those results, but for example, in the fluid mechanics work, we actually 3D printed. It's very difficult to see, but this is a fluid device that we designed, and we 3D printed this to compute the flow of this material. So I'm not saying we validated every design, but at least the important ones where we need to do multi-material validation, That's a complete different set of slides that I did not show today. I focused mostly on neural networks and microstructural optimization, but we have separate slides that show topology optimization and its validation using both plastics and metals.
Okay, that's nice. Thank you. Thank you.
Sure.
I had one more question, Suresh.
Oh, no, feel free. I mean, I'd be happy to answer the question.
This concept of like repeated multi-scale structures, I'm absolutely certain that this is one of the organizing principles in biology, and the way
Right.
the way you've discussed it like shows a lot of promise in applying this to biology. I had one question. You showed one way to do this, which is using the Voronoi structures.
Correct.
And that is like probably just one scale. Now, if I want to go from one scale to the next scale where the length scale, characteristic length actually changes, so how do you actually do it in a multi-scale way?
Excellent question. So you met Rahul Padi, right?
Of course, yeah.
So that's his PhD topic. So he's putting together a PhD topic on not just two scales, but multi-scale, truly multi-scale, going across different scales and multi-physics. So you have fluid flow, thermal convection, and you want to do osmosis. You want to do, of course, you won't be able to achieve all that, but he wants to set up a framework where we can answer this question, say, what do we need to do so that we can get to that point, given enough computational resources, we can mimic nature in a true sense. So, I mean, you go all the way back to the slide here and say, I mean, this is absolutely not reachable today by our engineers, right? This is a multi-scale, probably 4 orders or 5 orders magnitude. We can't achieve this today, but that's the direction that we want to go. And we're developing tools to get there. So the answer is we're going to use neural networks at different scales. So one neural network will work on the lower scale, the next neural network will use that information, and the next level, and so on and so forth. Is a cascaded neural network that we are visualizing to answer this question that you're asking.
Wonderful, yeah, very exciting. Looking forward to some papers on that.
Yes, yeah, me too. And I hope it's a very interesting area of research. It's not easy.
So this sort of multi-objective end-to-end topology optimization, how do you think this can be addressed using quantum computing or quantum annealing, which is probably what you have at the end?
Yeah. No, I did not put together as part of these slides because I figured I'll run out of time, because as it is, I rushed a lot. Usually this is almost like a 1-hour talk. And again, anyway, to answer your question, the computational resources that are needed to solve these kind of problems, or even these, is enormous. And it can take 8 days of computation on a computer cluster to do it. So the goal is quantum computing has a promise of exponentially increasing the speed up, as you know. And but we're not there as yet. Theoretically, people think, or researchers know, theoretically it can be done. But in practice, we have too many hurdles today that we can't achieve that today. So the goal for our group is, what do we need to push from engineering perspective to help achieve that goal? So we made very, very tiny toy problems just to give an idea what we're able to achieve. I don't know if the screen, does the screen appear at all? Probably not. I'm showing a different PowerPoint slides.
We can't see. We are still on the same
fine.
PowerPoint.
Yeah. That's fine. I will take 5 seconds to share a different slide. So this should show up now. Does it show up?
Yes, yes, yeah.
So this is an example of another question that they asked about topology optimization in 3D. That's a full 3D topology optimization that we developed, our tool. And you need to solve hundreds of matrix problems, a million degrees of freedom each. And you can imagine how long that will take on any given clusters. And this is not real time. It's taken probably 3 hours to solve this. So the question we're asking is, can quantum computing accelerate topology optimization? And we're taking baby steps. I'm not going to go to the details, but we're looking at this quantum annealing approach that we're taking. I'm also taking a quantum gate approach, and we're just taking some baby steps. So this is like the toy problem that we were able to solve on a quantum computer today. So it's like a 5x5, 6x6, really, really small, but it's like taking baby steps to hopefully one day, with the help of physicists and mathematicians and computer scientists, will help crack this problem of exponentially going faster to design multiscale structures.
Any more questions, anyone? Thank you, Suresh. That was really wonderful.
Oh,
I
thank
think-
you, and my apologies for losing the time that we did. But and again,
we just wish this can go on for a little bit longer. Actually, so much to learn from you. Definitely enough. I think for another talk that we will invite you again.
Sure.
I would like just to propose a short vote of thanks. First and foremost, I'd like to thank Professor Suresh for agreeing to deliver this talk very early in this morning, Wisconsin time, keeping us engaged with this talk on end-to-end multi-objective optimization of multi-material topologies and multi-scale topologies using neural networks. I'd like to thank the SASTRA management, especially the Honorable Vice Chancellor, Professor S. Vaidya Subramanian, Dean Planning and Development, Professor S. Swaminathan, and the Registrar, Professor R. Chandramouli, for generously supporting a visit to Professor Suresh's lab at UW-Madison during the summer. I'd also like to thank the Dean of SCBT, Professor K.S. Rajan, as well as the Chair of UW Mechanical Engineering, Professor Darrell Thelen, for their kind support. Thanks to all the participants of this talk. Thank you very much.
Thanks, everybody. It was all nice connecting with you. I hope the talk was informal, and again, feel free to reach out to me if I can be of any help to anybody.
Thank you so much, Suresh.
Take care.